Hello, my name is Olivier Clerc. I am a cardiologist from Switzerland, and I have been in a PPCR program for 4 years now. And for the TA workshop, I would like to present you a topic that I find particularly interesting, stimulating, and actually quite fun to do, which is machine learning. This is now quite trendy. This is being used in many domains, and it can really help to achieve unprecedented results for predictive modeling particularly, and this is where it is used also in medical research. I chose this image as a title because I think that machine learning is not only about computers, this is also about doing the perfect blend between human intelligence and computer intelligence to reach these new results that are completely fascinating. So let's have a look at it. What is that? What is machine learning? Well, obviously, this is a field of artificial intelligence because the computers are kind of thinking by themselves. This is using statistical techniques. So you are basing your analysis on statistical associations, analyzing the data. Actually, initially it was called statistical learning. But the point is that algorithms to perform this analysis are created by humans. So you could also say that maybe the most important part, the most intelligent part of the system is the human who created the algorithm. And the computer is just following the program, doing things as planned. But actually, the computer has a set of rules to learn by itself without very detailed programmation, but just with this set of rules and kind of find by itself the best option, the best predictors, the best model. And so it can improve the task what it is doing and provide the results that looks very intelligent, that seem very impressive. And this approach is totally explorative and again, data-driven, based on statistical associations, but not based on hypotheses, not based on causality. So sometimes you have to be careful if the computer finds an association, that does not strictly mean that there is a true causality there. And the whole procedure is very computer intensive. It takes very complex calculations. Some of the most complex models, if you would print them, it would like cover all the walls of the room. So it's something you cannot really understand, read in details, but the set of rules are clearly established. And there is more emphasis on the calculation and the domain expertise is not so necessary because you are analyzing this with statistical rules. But still knowing a little bit about the topic can help to make better models. And as previously mentioned, you can really use this to discover new structures in the data, to create new prediction models that have an excellent predictive accuracy and that help to make decisions also in clinical care. Again, I think this is a very interesting blend of human intelligence and computer processing. So this is not only about machines. And why is that useful? Well, the thing is you can integrate all the available data. You can have a huge data set, big data, millions of predictors. The machine is going to be able to handle that. It may take a bit of time, but it's possible. And it makes calculation that would be totally impossible for humans, even with a calculator. This is way too complex. It would take years. And the computer can by itself, depending on the model, do variable selection. So find the best predictors, help you to build a model. And again, create predictive models that have an extremely high predictive ability. They are reproducible, they are quantitative, they are quite explicit, so you can understand how the model was built. And you have many different approaches, many different algorithms. So if one algorithm doesn't work that well on your data, no problem, try another one, try many other one, and choose the one that works best on your data. And that's actually all about it. There is not like one algorithm that is perfect. There are many of them, and you try several of them and find the one that is the best for you in your question, in your data. And you can, again, find novel insight, novel patterns. And sometimes you can also discover causalities with these associations, but you have to be careful about that. You can automatize the process. So you can ask the computer to gather the data and analyze it by itself without doing anything. You just have to code it first. And it is used, as previously said, in many, many domains. Also now in research, particularly medical research, but many other topics are interesting, such as, for example, image recognition, which is currently quite trendy. And the only drawback of machine learning is that the most complex models are really difficult to understand. You understand the rules, but it's difficult to explain why the models comes to a given prediction. So it has a little bit of a black box feeling. That's the drawback of it, but you get a better prediction. And so let's have a look at the types of tasks that you can do with machine learning. There are three main types: supervised, unsupervised, and reinforcement learning. What is that? Supervised learning is the thing that we'll be focusing on, and it is most used in medicine. This is when you are trying to construct, for example, a prediction model based on data for which you know the outcome. For example, you have a data set of patients. Some of them had a myocardial infarction, some did not, and you want to create a prediction model for myocardial infarction on this data, so you have the outcome, and you will use this model in future patients to say which one is going to have an infarction. So you have a task, you want to create a model, you know the outcome of the data that you are using, and those tasks can be called classification or regression tasks. But beware, because there is some specific wording for machine learning. A regression task does not mean that you are using a regression. It just means that the outcome is a continuous measure. And a classification task means that the outcome is a categorical measure or binary measure. And by contrast, unsupervised learning is when you have a bunch of data, but you don't have much understanding or theory about it. And you would like the computer to find groups, find clusters, find patterns in the data, maybe simplify the complexity of the data to better understand it. And that can be quite helpful in explorative analysis. It has been done, for example, in heart failure with preserved ejection fraction, because this is an heterogeneous disease, difficult to treat. And so it was possible to identify a cluster of patients with similar characteristics that might respond to similar treatment. So it has also usefulness in medicine, even though supervised learning is more used. And reinforcement learning is something quite different. This is about learning a practical task. Imagine a robot that has to do something, maybe construct a car, and it learns by trial and error. So it tries to make a step, and it was good, so it receives the feedback good, and it tries again a bit differently, that was bad, so it gets the feedback bad. And it does many tries, it tries many possibilities of the ways to doing it, gets feedback and integrates it and find after many tries the best perfect way, the best move to do its task. For example, it has also been used for video games. The computer can try to do the game. So at first, the computer is catastrophic because it does not understand the game. It just tries every possibility. So a child would be better. But after playing the game 1 million times, the computer will have found the perfect run to the end of the game. And this is also used for driving, or there are funny videos on the internet, like a robot that is trying to toss pancakes out of a pan. At first, it is catastrophic, but at the end, every toss is perfect. But this is not really something that we use much in medicine. So once again, I just wanted to come back to this task to really make it clear. So if you have unsupervised learning, as you see on the left, you are trying to find groups in the data. Supervised learning, you know the outcome, but you want the computer to create a prediction models to predict this outcome in future data. And reinforcement learning is really the computer learns by trial and error to do a task. For example, there is a famous data set for machine learning and predictive modeling with the iris flowers. And there are like 3 species, and they have different length of petals and sepals, so they have different measurements. So you can go supervised, you can tell your computer all the measurements and the name of each species and make me a prediction model for the species, and it will tell you, well, if the flower has petals like this or like that, it will be this species. If petals are like that, it will be that species. And then if you bring another flower, the computer can tell you what is that for an iris. Or you can go unsupervised, like I have a bunch of flowers, I don't understand anything, please find something. And the computer will find that there are 3 clusters of flowers with similar characteristics. And those are actually the 3 species of iris in the dataset. Of course, this is not really useful for medicine, but it's to help you to understand the difference between supervised and unsupervised. And again, about classification and regression in supervised learning, regression is not about using a regression. This is about having an outcome that is a continuous measurement, and you are trying to fit a function that goes through the data. Whereas a classification, you are trying to find a separation that will separate your data between patients with or without the outcome. Now, a few explanations about model fitting. If you have a look at those models here, you have the same data points and 2 different lines for 2 different models. Which one is the best one between the 2 here? I think you will clearly say this is model B, because the line is much closer to the dots. It fits the data much better. Why? Because the distance between the dots and the line, which is here in purple, is smaller. So this distance is the error, the difference between the prediction and the reality of your data. And the whole goal of modeling is to find the model that has the lowest error, to minimize error. To calculate error, it depends a little bit of your outcome. If you are with a continuous outcome or categorical outcome, you can use mean squared error, misclassification, log likelihood, entropy, many things. This is those details. I don't want to go too deep into the math, but just the concept. You try to bring the function as close as possible to the reality. Some simple functions have calculation that allow to calculate right away what's the best fit, but frequently they have to go step by step, kind of like a reinforcement learning. Try a model, calculate the error, try a different one, see if the error is higher or lower, and so on, and keep improving the model progressively until the computer has found the perfect fit. This is what the computer is doing when you do machine learning. It does thousands, millions of calculations to find the best model for each, the best fit for each model. And this is quite important to speak about fitting because this is a key aspect in machine learning. This is the question of underfitting versus overfitting. Maybe you have already heard these words. So on the upper row, you have the regression task, so continuous outcome, and on the lower row, classification task. So in this case, a binary outcome. So in a regression task, you want to fit the data closely, and in a classification task, you want to separate the data. So if you start on the left, you do a model that is too weak, that is a bit stupid. You are just putting a line anywhere. And as you can see, it does not follow the data. This is not a good prediction model for neither of the two tasks. In the middle, you have actually a good thing, a good fit. It's following the data. It's grasping the concept. It's not perfect. There is one misclassification, but overall, it does a good job. And on the right, this is what happens when you go too far, when you do overfitting. Overfitting is when you are looking so closely at the data that you find maybe random association, random noise in your data, and you integrate it into the model. And this may be an excellent performance for prediction within your data set, but as soon as you want to use it elsewhere, it will be very bad. For example, again, with myocardial infarction, I'm a cardiologist, so let's go with that. You start with a stupid model. You say, for example, men are going to have infarction and women will not. This is not completely stupid because there are differences in risk, but this is way too crude. I mean, you are not going to have a good prediction model with that. So maybe you will add many more things. You will add age, smoking, diabetes, blood pressure, cholesterol, and so on. And you will get a model that is more in the middle. That's quite good. It's not perfect, but it's doing a good job. And maybe by chance in your data set, people with blue eyes have more infarctions, maybe. And you know what? Your machine learning model will see it and will take it into the model. And it will be excellent because on your data set, it will help because this is a true prediction within your data set. But when you try to take your model to another data set, it will be catastrophic because this prediction of infarction in blue eyes is totally wrong. So that was overfitting. You have to find the right spot between simplicity and complexity to have a model that is good, maybe not perfect in your data set, but that is reproducible in further data sets. And this is actually formalized here by the Bias-Variance Tradeoff. This seems complicated, but don't worry, it's just the same concept. On both of these graphics, you have on the x-axis the model complexity. So on the left, you have a simple model that is underfitting, and on the right, a complex model that is overfitting. And the sweet spot is in the middle to balance actually the fit. And the question is, what happened when you are on each of the sides? So on the sides, on the left, you see the red curve is the total error. So you see the minimal error. So the best prediction is in the middle. And on the side, you have high error, bad prediction. But what happens on the underfitting side? You have a high green curve, high bias, and low variance, which is the blue curve. That means the bias is the difference between your prediction and the reality. If your model is too simple, it's just bad. It's far from the reality. But it will perform always the same way across all data sets. It will be equally bad all the time. So that's high bias, so very wrong, but low variance, very stable. On the other side, if you overfit, if you go too far and include random noise into your model, your prediction might be fantastic in your data set, so low bias. But as soon as you use it in another data set, it will be catastrophic, unstable, high variance. And this means that the error in overfitting comes from variance and the error is underfitting comes from bias. Note that this word variance, this is not variance in statistics. This is again a specific wording for machine learning. And on the right side, this is the same concept applied to the performance in your original data set, the training data, and in another data set that you use to check your result, the test data set. If your model is underfitting, not detailed enough, it will have high error, bad prediction in any data set. That's on the left side. And if your model is overfitting, too complex, it will have very low error. So high performance look very nice on your data set that you used for training. But when you use it on another data set, you will have a huge error. It will be very bad, high variance. So this is why you have to find the sweet spot of a model that is good, but maybe not perfect on your training data, and it will be reproducible on other data sets. And this is actually the key reason. This is one of the goal rules in machine learning and generally in predictive modeling, is that you need to have several data sets, because having a good prediction does not mean that your model is good. Maybe you are just overfitting the data. So what do? The luxury version is to truly have several data sets. You have your data set and maybe an external data set from another center. So you can use one to train the model, to develop the model, and one to test the results. But frequently you don't have that. You have just one. So you have to split your data set into two subsets. One training set, usually like 70 or 80% of the data, to create the model, to train the model. And the testing set, you just keep those patients aside. You don't touch them. You keep them for the final testing at the end. You do not develop the models on them, because you want to have a fresh data set to see if you were overfitting or not on the training set. That's kind of one of the core procedures in machine learning. And actually, there is one more level of complexity, is that many machine learning models exist in many versions. They have so-called hyperparameters. Those are internal parameters. You have many different versions. You can try different numbers, and it will affect the performance of the model. There is no one ideal parameter. You have to try many of them and see which one works best on your data. So to do that, you must reproduce the same concept of training and testing, but within your training set. So you have to divide your training set into a true training set on which you develop the model, and a validation set, which is actually another testing set within the training set, on which you will try all the variants of the model. And when you have found the best version of the model, you will test the final version of it on the holdout testing set that you have kept on the side at the beginning. It sounds a bit complicated. So let's come with an example. You want to predict, again, myocardial infarction. You want to do 3 models. Maybe you want to do a regularized regression, a decision tree, and a neural network. Each of them had hyperparameters. So you will train different versions of each of these models within your training set, and choose the best set of parameters for each of these models using validation. And then you will have like your best regularized regression, your best decision tree, and your best neural network. You take them, and then final round on the testing set, which one of the 3 performs best. That's how it works. Now, this validation within the training set, there are many methods. You could actually have a fixed validation set and a fixed training set, but that's not so good. Actually, to have the highest possible power within it, you use some resampling methods. The most popular one is cross-validation. Usually you do it with 10 folds, but on this example, it's simpler with 5 folds. What do? You take your training set, you cut it into 5 blocks. First round, you develop the models on blocks 1, 2, 3, 4, and test the result on block 5. Second round, you develop your model on blocks 1, 2, 3, and 5, and test it on block 4, and so on. So you do 1 round for each block on which you will test the data. So every time you develop the model on all blocks except 1, and this block you keep it to test your data. And then you average the predictions during all those folds of cross-validation, and that gives you the average performance of this version of the model with this set of parameters that you will then compare with other versions of the model with other sets of hyperparameters. So for example, if you do 10-fold cross-validations and you have 10 numbers that you want to try for one hyperparameter, you will try 100 models. If you have like 100 values that you want to try in 10-fold cross-validation, you have 1,000 models, and so on. And if your model has maybe six hyperparameters and you try 10 values for each of them, it will do a lot of models. So your computer is going to work for a long time. And this is actually what computers are doing most of the time when you are fitting models. They are just doing resampling and testing, retesting until they have found which is the best set of parameters for each of the candidate models that you are trying. And another approach, which is similar in the concept, but approaches differently, is bootstrapping. Instead of making fixed folds within your data, you just draw randomly patients from your data set with replacements. So maybe you will draw the same patient several times, and some of the patients, maybe they will never be drawn. So you generate similar data set that have the same patients, but some of them are multiple times there or not there. So it's both similar and different. And you can test the performance of your models within these different Bootstrap samples. And then there are different options to test the performance. Either you have a validation set within the Bootstrap, or you use patients who have not been drawn into the Bootstrap as validation. This is called out of bag. Or you can actually compare the prediction in the Bootstrap versus in the whole training sample, and this is called optimism correction. And anyway, in the end, you do many tests, you average the performance, and so you can know which set of parameters is the best for the model that you are testing. Now, I just would like to speak briefly about the question of data dimensionality. It sounds very complex, but this is just about what is the ratio of observation to features. Observations would be like the number of patients, and features in the machine learning wording, that means predictors like risk factors. So in a standard data set, maybe you have 1,000 patients and each of them has 20 risk factors that you want to try as predictors. That would be low dimensional because you have relatively less information on each case than the number of cases. And in this case, actually, all models should work. Some of them will work better than others. And actually, gradient boosting models are particularly powerful in low dimensional data, but all of them could be good. And now the contrary is high dimensional data. Maybe you have 100 patients, but you have detailed genomic data. You have 1,000 different genes on each patient, and you have 100 patients. So you have more information on each patient than number of patients. This is also true for image analysis, because you can imagine one image is like millions of pixels, and each pixel is one information for the computer. So it's high dimensional data. And this is a situation where some models will not work, just like regression, this is not possible. But fortunately, other machine learning models are very effective at that. And the ones that are particularly good are neural networks, also called deep learning, because they are able to see patterns in highly complex data. They may not be particularly effective in low dimensional data, but truly they shine in high dimensional data. Other approaches, you can maybe reduce the complexity of the data with variable selection or with principal component analysis, where you try to merge different predictors into a lower numbers of predictors with the matrix algebra. So again, just to summarize the process of machine learning, you get your data set. First, actually, you should prepare your data. That's still another topic. Sometimes you have to reformat some things. This is feature engineering. And then you split your data set. You have a test set, you keep it on the side, and a training set. And within this training set, you are going to do training and validation. For example, you can use cross-validation. So actually, you don't have a fixed validation set, or you have a dynamic change in what is used for validation and training. You test all the sets of hyperparameters that you want for each of the candidate model. You come up with one best candidate model, one best regression, one best decision tree, one best neural networks, and so on. And then you compare them on the test set that you have kept on the side. This is the final round. And then the winner, maybe you will find the neural network is the best in this case, but maybe in the next data sets will not be so. In this case, it's the best. And then you can use it to predict outcomes in future patients. So that's basically the procedure. Here's just to introduce. Now we are going to have a look at a few models that I find particularly interesting. There are many of them. Theoretically, some of them perform better for some types of tasks, but in the end, you have to try many of them and see which one does best with your question in your data. So we start with basic regression, and that's a good news because maybe many of you have already been doing machine learning without knowing it, because regression is machine learning. You are basically asking the computer to find the best fit through the data or the best separation to classify the data. So that's machine learning. These models are relatively simple compared to other models. You have linear regression, for example, for a regression task. So regression task means continuous outcome, and logistic regression, which is focusing on the log of the odds. So you can recalculate it for probabilities, and then it becomes a sigmoid function, as you see here. This is for classification, particularly for binary outcomes. The problem is that they have strong assumptions on the structure of the data, linearity, and so on. So they are not very flexible. They have tendency to have a high bias and low variance. So they are stable, but you can have something better as a prediction model. And they don't have any hyperparameter to tune the models. So you don't need cross-validation for them. But if your data are truly linear, then they may perform very well, so that's worth trying them. But for regression, you can go further. You can, for example, use those regularized regression. They are also called penalized regression because you have a penalty factor, which is called lambda. What you are doing, you are trying to minimize the error, so the difference between your prediction and the reality, plus the penalty. How much should be the penalty? You have to try many values. Maybe you try 100 different values in cross-validation to find which ones works best on your data. And there are different approaches to regularization. They actually do a penalty on the coefficients, on the regression coefficients. So if you have high coefficients, you will get a large penalty. So the system will try to reduce the regression coefficients, and it will first reduce the regression coefficients that are not really useful. So it will help to focus the regression on the most useful predictors and to kind of shut off the ones that are less useful. And if you do ridge regression, the penalty is focused on squared coefficients. So you square the coefficients, so they cannot be negative. And this will have a bigger effect on large coefficients because large coefficient will get very big with squaring. So it will make the coefficients more uniform. It will not exclude them, but it will be very useful if you have correlated variables because it will help to sort them out. And as you can see on the graphic on the left, as lambda increases on the x-axis, you have the values of these predictors. They don't change, but if the penalty gets high, the predictors start to come towards the zero line, which is in the middle. So they are kind of homogeneously coming nicely together. And this is ridge. The other one, which is very trendy, is called lasso. It is the same concept, but it penalizes the absolute coefficients. The demonstration is a bit complicated, but the fact is that when you do that, the model will shrink the coefficients to zero. So it will perform variable selection. It is actually a very good approach to do variable selection, much better than stepwise regression. Forget it. If you want to do good variable selection in regression, just do lasso. And you see it on the right graph. As the lambda increases on the x-axis, you see first the coefficients in the different colors, they don't change. But when the penalty gets too high, suddenly the coefficients, they crash to this zero line in the middle because this is those predictors have been excluded, and the strongest one stays until the end, but the less strong one, they are excluded earlier. And again, what is the best lambda factor? You don't know. You have to try many of them, cross-validation, and find the one that works best on your data. And there is actually a third version, which is called elastic net. This is simply a mix of ridge and lasso. And then you have lambda and also an alpha factor that you can tune, which is the mixing parameters. Do you do like a ridge and lasso 50-50 or 25%, 75%, and so on? You can try different mixing factors and see which works best in your data. But the thing is, you can also go with more complex regression that are not linear, because your data, maybe they are not following a linear pattern. As you can see on the left, clearly you need a curve function for that. So there are many approaches, but one is called generalized additive models. It's a bit complicated. It has many methods that can fit a smooth function that is non-parametric and that can follow such nonlinear data. You can choose between different methods for fitting and with or without variable selection. That's nice, but these models are a bit slow, so you have to wait a lot. It's a bit annoying. And I prefer much more the right one, which is called MARS, Multivariate Adaptive Regression Splines. This is actually a copyright, so many software call it Earth because they are not allowed to call it Mars. That's just for the funny thing. And what it does, it is also a regression, but it uses linear splines. It sounds complicated, but this is a function that may say, for example, for age, up to 50 years, the outcome remains zero. And starting at 50 years, it begins to be a linear function, like 2 times the age increases the outcome. So it makes functions that have an angle, that have a knot. And if you add many of them, you can have a function that have many angles. As you see on the right, the Mars is able to use angles to fit to the data, to follow the data points, to be very close to them. Of course, the problem is that it is prone to overfitting. So you have to, in the algorithm, the algorithm is going too far, making a function that is clearly overfitting, and then it is progressively excluding predictors, pruning back the function to a simpler one find the good sweet spot. And this is also something you want to tune, how many predictors you want to keep. And another fantastic thing in this model is it automatically explores interactions. So it does not only test every predictor, it tests combinations of predictors. So you can really find fantastic things in your data. With other regression models, you have to specify interaction, specify if you want to have like second or third powers of your data. With Mars, it will just check everything. This is something you can also tune how far you should go with that. Very, very powerful model that I highly recommend, Mars or Earth. But now let's change worlds and go to something completely different, decision trees. Because sometimes if regression is not working, you need a completely different approach to the data. And decision tree is basically finding splits, trying to separate the data into subgroups that are homogeneous. It was originally called classification and regression trees because it can also do a regression task, so a continuous outcome, but this is mostly used for classification. And it actually searches through all predictors how to separate the data and to actually maximize purity, so maximize homogeneity within subgroups, which is a reduction of impurity or improving the impurity change formally with the Gini index or entropy or squared error. The interest of the thing is that it is very nonlinear and it focuses on interaction. So actually each additional split is an interaction if you think of it, because based on the fact that the patient is a male, the next best cutting point would be age. So this is actually, if you think it in a regression framework, this is interaction. And the advantage is it makes very simple models. So if you look at this model, this is a model from the Titanic dataset trying to predict survival. So you see, in the end, the model is very simple. Is it a male or a female? And then is age more or less than 9.5? And then is how many family members were on board? And then you have a prediction about survival. For example, you can try it with the characters of the Titanic movie. If you take Rose, is sex male? No, probably survived. This is true. And if you take Jack, is sex male? Yes. Is age more than 9.5? Yes, probably die. This is also true. You see, not bad. But the thing is, those models, they are very simple, very easy. You can use them at the bedside, or you could go to the Titanic and say, you are going to live, you are going to die. But overall, the performance is not so fantastic. You need to go a bit further. There is also tuning parameters, because you can also keep finding splits into the data and go too far and overfit. So you have to limit, for example, tree depth or node size, or maybe you use a complexity threshold, which is kind of a penalty for additional nodes, where you have to minimize misclassification and this penalty for additional nodes to find, again, the sweet spot between going too far and overfitting the data and going not far enough and underfitting your data. And always with cross-validation or bootstrapping or resampling or whichever technique you prefer for validation. So what can you do with decision trees if you want a better performance? Because this is actually the first step of a family of models that have very different approaches and can be very powerful. The first improvement is to use Bootstrap aggregation with bagged tree. Bagged means actually with Bootstrap aggregation. What do you do there? The problem with a decision tree, you have one tree on your data. This is a bit weak. You would like maybe to have different trees that look at the problem from a different point of view and then average their predictions. That's the concept. And to do that, you do bootstrap sampling. So you make those bootstrap samples. You take sample of patients which are similar but a bit different to your basic data set. And on each of the bootstrap, you fit a tree. You can go for an overfitted tree, way too detailed, lots of overfitting. This is not a problem because in the end, you will average the prediction for maybe 500 trees, and this will deal with overfitting. So this will be more powerful than one single tree. But the problem is that those bootstrap samples, they tend to be not so different from each other. So you would like to have more variability between your trees, more different viewpoints on your data. And this is where the next refinement, which is called random forest. This is a well-known model and quite powerful, actually. Basically, this is the same idea of bagged tree. You make bootstrap samples, you make a different tree on each bootstrap, but you add one rule, which is you limit the number of predictors that the tree is allowed to use. What is the best number? You don't know. You have to try. This is a hyperparameter. You can try different numbers. You can also try different depth of the tree and so on. A number of trees. You can try many things. But the idea is, for example, if you limit to 5 predictors out of your 20 predictors, your first tree is only allowed to use 5 predictors, make the best tree possible with those 5 ones. The next tree will get another random set of 5 predictors, and it has to do the best tree with those 5 predictors. But this next best tree will be different than the previous tree because you are using different predictors. So that's actually a trick to force the system to make very different trees, look at the problem from different point of views, and then when you average the prediction, you get something very interesting and very powerful. It is also very good to have a look at feature importance, so which predictors are really predictive or not, because you can have a look at how the trees use the parameters, because they may be allowed to use 5 of them, but maybe only 2 or 3 are useful and 2 of them will not be used because they are too weak. Because one of the things I didn't tell you, this is like with the decision trees, the thing is it does variable selection, because it always takes the next best cutting point, but it does not have to use all the parameters. So effectively it does variable selection. And this is the other refinement, very, very powerful refinement to decision trees. This is kind of one of the most powerful models you can have on low dimensional data. This is gradient boosting. This is actually the contrary. Instead of doing many very large overfitting trees in parallel in different subsets, you do the contrary. You do very small underfitting trees that come in sequence. So what do you do? First, you start with your data and you do a very simple weak tree that has a weak prediction. And then the very important thing is that the next step, you are not trying to model your data, you modify your data and you give a higher weight to the patients who had a wrong prediction. So you are overweighting the error of the previous tree, and then comes the next tree, has to improve this result. Then you calculate how wrong, how true it was. And then again, you apply new weights, you are overweighting the error in prediction, and each tree has to come in sequence and improve the prediction that has been done until there. So I can have a sequence of hundreds of trees. Each of them is weak, but improves the prediction that has been done until there. And in the end, you have a very, very, very strong prediction. Actually, this is a very fantastic idea, and that works very well. There are some very powerful models out there. One of the first was AdaBoost. But the ones that really showed the power of the methods were first gradient boosting machines, which is a little bit slow, and it was accelerated and improved into a very trendy model, which is extreme gradient boosting, XGBoost. It became famous, for example, it was very essential to find the Higgs boson because it was difficult to classify noise from true information from the detectors. And actually this was, they used XGBoost for that, and this became famous for this. And this is now very frequently used for machine learning competitions. So this is kind of a choice of champions. Other very powerful models that are new are CatBoost and LightGBM. So clearly I would recommend you to learn about these models. The tuning procedure is a bit complex because they have many tuning parameters. You have to do several rounds of tuning, typically do like 3 rounds with several parameters and then a final round, but it can take like half a day to fit a model. So it's a big thing, but the quality of the models is fantastic. Now let's change family. Let's move to the neural networks, which are also called deep learning when they are very complex with many layers. What is that? This is actually a set of activation functions that are interconnected with weights. It sounds very complex. You could almost compare it to many logistic regressions. And they are interconnected. So each function is receiving input, so values from many other functions, and they will react a little bit like a neuron with a action potential. So they will sum up information and then filter the information and then fire a signal, maybe a bit modified or different. So this is similar to what neurons are doing. So the specificities are the multiple interconnection between all those functions, and this ability to kind of store, modify the data and then send it further. So this is really something that is particularly useful in high dimensional data, because this is something that helps you to find patterns in the data, to find on an image. If you look at each pixel separately, maybe only neural networks would be able to find a face or a cat or a bird on the image. because this is something, a very complex pattern that is best captured by such a structure. There are many different architectures. Sometimes you have neurons that are interconnected with themselves. You have memory cells. You have maybe structures where you have first many neurons and then less. It's like convolutional structures. This is a big topic. And how to fit those models? Actually, you send many data to the model. You start with kind of random values for the weights. The weights are actually the coefficients of each connection. But for neural networks, there are other words like weights is for coefficients, input is for predictors, and output is for outcome, but it's basically the same, just with different words. You send many data to it, and then you analyze the performance, and then there is a backpropagation algorithm or other algorithm that will modify the weights according to the quality of results and say which nodes should be modified and which weights should be modified, and then try again, compare the results with the theory and with the real data actually, and the prediction, and change again. So you do many epochs. You send your data, you check the results, you adjust the model, you send again data to the model again. So this is kind of a reinforcement learning actually. And the tuning parameters, they depend actually on the type of tree that you are using, but basically you can choose the number of layers, the number of nodes per layer, the learning rate, which is how fast the weight will change, if weights can be set to 0 with weight decay, in which direction they will change with momentum. And again, it depends on the model that you are using. This is a huge topic in itself, but it's an interesting model for high dimensional data particularly. Now, another one that is quite crazy but interesting, this is called support vector machines. This is a family of models that have been created for classification tasks, but now you can also do a regression task with them. And they can sometimes be useful when you want to classify something and the other models fail. So sometimes it works well, sometimes not. For example, if you have a look at the data on the very left, if you would like to put one line through the graph to separate the blue, red squares from the green circles, you are not going to find a place to put this line. This is not working. But what you can do is to use a statistical trick, the kernel trick, to create a new dimension in your data. There are different formula like linear kernel, polynomial kernel, or radial basis function kernel. And as you see on the graph, with this new dimension, suddenly you can create a hyperplane that will separate your data and do an excellent classification. That's the concept behind it. Formulas are a bit complicated, but actually somewhat similar to logistic regression. There are also tuning parameters, such as cost, which is tolerance for errors, and some kernel parameters to set the shape. An interesting family of models to try, particularly for classification. There are many other ones. I just wanted to show two more for supervised tasks. One is called naive Bayes. This is using Bayes formula, so this is based on conditional probability. And you are basically just calculating the probability of the outcome using the prior probability of the outcome. Hypothesis here means outcome, and the evidence would be like the predictor. And you use the likelihood of the predictor given the outcome. The denominator, actually, you can ignore it in the formula, and you can only multiply all the likelihoods and probabilities to calculate the final probability. That seems so simple that it shouldn't work, but this is surprisingly powerful. And this is called naive Bayes because you ignore the fact that there could be an interaction dependencies between predictors. You just assume that each predictor is independent, which is certainly wrong. But again, surprisingly, it works very well. So do not ignore this model because you can really get good prediction with that, particularly if you have categorical predictors. Because if you have continuous variables as predictors, you have to use some kernel approaches to transform it to categories. This is one of the tuning, well, two of the tuning parameters actually, like kernel parameters. And this Laplace smoother as a tuning parameter is important because just imagine one of the probabilities is 0. That would kill your model because this is just a multiplication, and then the whole model would be 0. So what you can do is, for example, add 1 or 2 or one number to each of the numbers to avoid that your model is becomes 0 if one of the probability is 0. That's just that. And the other one is k nearest neighbors. This is actually a conceptually quite simple model. The calculation is not so complicated, but it uses actually distance. So it measures differences between patients in your data using like Euclidean distance, for example. And what you do is that you do a prediction for a patient based on the categories of the outcome of the nearest patients. So you look which patients are most similar to this one, and you decide that the prediction for this one is like the majority category of the closest people. How many closest people you should consider? This is a tuning parameter. This is this K. So you try different values. For example, if you see on the graph, we want to predict the class of the green dot. If you are trying K is 1, then you consider only the nearest patient. So this is the blue square. So we predict that the green one is actually blue. But if you are trying 3 as K, then you will consider the 3 nearest people. You have 2 reds and 1 blue. So your prediction for this new case would be red in this case. This is how it works. And actually, sometimes it works well for prediction, sometimes not so well, but it is very good for imputing missing data, because you can find similar patients and impute missing data with that. So it's quite interesting. And then we move to the next level. What can you do when you have a supermodel with a good prediction? Actually, you have several of them. You can mix them together. You can put like a new level of machine learning. You take the result of each of your separate model and you do machine learning on that for a new level of prediction to go even further. This is called model stacking or super learners. Sounds super fancy. It works quite well actually with like regression, with relatively simple models to aggregate them, because if you aggregate them with complex models like boosting, surprisingly doesn't work that well. But the thing is this approach is kind of standard in the competition for machine learning, because this is the way to get the very, very, very best prediction for the model and the way to win a competition. But it cannot, sometimes not so useful in practical situation, because the improvement is so small. It's nice for a competition, but for practical predictive purposes is not really useful. And I just wanted to just give you 2 examples of how modeling can look like if you are doing an unsupervised task. Like you want to find a pattern in the data, but you don't really have, you don't know the outcome in your data set. So this is basically, you are measuring differences between values. This is somehow similar to nearest neighbors, but here this is k-means clustering. So you create clusters by minimizing the within cluster distance. This distance is just the similarity of patients. So you are just calculating groups of similar patients using actually an algorithm that will recalculate with centroids. You see the 3 black dots are the centroids, and this is actually this data set with iris flowers, what I told you, and it has found actually the 3 species within the data set. And you can also do hierarchical clustering, where you create this dendrogram, which is a tree graph where you can measure actually the similarity or the dissimilarity between individuals or group of individuals. This is quite interesting, for example, in genetics, if you want to see like strains of coronavirus, which one is close to which one, you can use hierarchical clustering. There are, well, different methods. We won't go into detail, but just to tell you that it exists. And now how to do that? Actually, it may all seem very complicated, but it's not so difficult to do. There are so many softwares to do it. The one that is most frequently used today is Python, which is a statistical language, but R, well, actually it's a computer language, not only for statistics, Python. It's a general purpose language, while R is more purely statistical language. It also works very well for machine learning. And there are many other ones, software, some are free, some are not free, but there are really lots of options and some packages to do special thing and extremely powerful model, just like Keras and TensorFlow for like neural networks. A few sources, there are many things on the screen. There are plenty of books, plenty of websites, plenty of internet courses to learn machine learning. Some are free, some are not. A few websites that you might check out, for example, Kaggle. This is a website for competitions, but you can also learn machine learning there, like Towards Data Science, Medium.com, Machine Learning Mastery, and so many others. Courses can be found on usual platforms like edX, Coursera, Udacity, Simplilearn, or there are also specific courses maybe on DataCamp, which is focused on R and Python. And among the books, I just wanted to specifically mention 2 of them. The first one, The Elements of Statistical Learning, has kind of founded the field. So it's like the reference, the basic, but it's a little bit difficult to read. So there is an easier version, which is called An Introduction to Statistical Learning. This is the second one by, in part, the same author. So I would recommend this one, the second one, to start if you want to read a book about it, to understand a little bit how the models are working. This is more about the math behind it, but explained in a way that is understandable. And if you want to really learn how to use this to code in Python, in R, and so on, then you should more have a look at the other books or at courses for the practical aspects. But the thing is, this is definitely not as complicated as it may seem. You don't really need to be a mathematician for that. You need to understand how to code, how to ask the computer to do the task, and the computer will take care of the calculations, even if you don't really understand them. So I hope that I could convince you that machine learning is a really powerful set of methods. You can explore data, you can discover insights, and particularly you can create very, very strong prediction models, and you can have a lot of fun with it, trying many things. This is now very widely available. It's not so difficult. You can learn it even for free. So just don't hesitate to start doing it if you have a little bit of interest in predictive modeling. I wanted to leave you with useful citations in predictive modeling, like all models are wrong, but some are useful. No model is perfect, so that's the reality. And what about, I told you, be careful with interpretations of your model. Is like a biologic interpretation can be found for any model. So just be careful and don't go too far with interpretations. And again, about the sweet spot between overfitting and underfitting, a citation attributed to Einstein, everything should be made as simple as possible, but no simpler. So I leave you with this funny graphic of what curve fitting methods tell about your personality and the message you are sending. It's not exactly machine learning with the methods I showed you, but this is somewhat similar and it's funny. If you have questions about it, I'm happy to answer. If you want to contact me, I think I have been speaking way too long as usual, but I find it very interesting and I'm happy to talk about it. So, well, I wish you all the best and goodbye.